everyone, welcome to the course Mathematical Aspects of Biomedical Electronic System Design. My name is Chandramani Singh. I belong to Department of ESE at ISC Bangalore. I'll take you through the first few modules of the course. Our first module will be on signals and systems. In this module, in particular in this lecture, we will see an introduction to signals and systems. We will see notions of causality, instability, linear time invariant systems. We will also see convolution, sum and integrals. We will see how LTI systems can be characterized when represented by difference and differential equations. Finally, we will see water transfer function and frequency response. Let us start with signals. Signals are functions of one or more variables. Here are a few examples. In its speed signal, the variable is time. In image, there are two variables, namely two spatial variables. In videos, we have time as well as spatial variables. In this course, we will restrict our attention to signals with one variable. The variable will be usually interpreted as time. Now there are two types of signals. A continuous time signal it depends on a real valued time variable, usually denoted as t. Here is an example. You might be familiar with this signal. This is called unit step signal, usually denoted as UT. So UT is 1, t is greater than or equal to 0 and 0. On the other hand, a discrete time signal depends on integer valued variables, and signal depends on a integer valued variable and that indexes instance of time which can be interpreted as an index of time. Rather, I would say as indices of time. Again, we can have examples. discrete time unit step signal that would look something like this. Denoted as UN, or another quite popular signal often encountered in analysis is Dirac impulse function. Unit impulse. This is typically denoted as delta n. So this is called a unit step. This is also unit step, continuous time unit step, whereas this function is called impulse or unit impulse function. Observe that the two are related, unit step and unit impulse. UN is accumulation of infinitely many impulses. Okay. Now let us move to systems. For us, a system is a process that transforms input signals to output signals. Input signals are transformed to output signals. Here are a few examples. So we may have a discrete time system, that takes a discrete time signal as input and outputs another discrete time signal. This would be called discrete time system, and an example of such a system would be a moving average filter. In which yn, the output at any time index, is a moving average of say 3 of the inputs. So this is an example of discrete time system. We can also have a continuous time system. Where both input as well as output are continuous time signals. An example of such a system would be an RC circuit. So here is an RC circuit with an input voltage xt, and we treat the voltage, capacitor voltage, as the output. We will use this example to illustrate many of the properties of signals and systems as we go along. Notice that in this continuous time signal, output and input are related as follows. Next is an important class of systems called memoryless system. A system is called memoryless if its output at a given time depends on the input only at that time. Called memoryless. Its output at a given time depends only on the input at that time. Depends input at that time. Okay. So here are a couple of examples. If we consider a simple register and treat the current IT as input, the voltage across the register as output, then Vt is RIT, and this is an example of a memoryless system. This is Vt is the output, IT is input. Clearly output at any time depends only on input at that time. So this is an example of a memoryless system. On the other hand, the moving average filter is not a memoryless system. Okay. Next we look at another important property called causality. A system is called causal if its output depends only on the input at present and past times, not on future times. A system is called causal if its output at any time depends only on the inputs at present and past times. Only on the inputs at present and past times, not on the inputs at a future time. Inputs at future times. Again, example. RC circuit that we described above is a causal system. On the other hand, the moving average filter is not a causal system. Let us now look at another important property of systems, namely stability. A system is called stable if all bounded inputs generate bounded outputs. On the other hand, if there exists a bounded input for which the output grows unbounded, the system is called unstable. If there exists a bounded input for which the output grows unboundedly, the system is called unstable. Let us look at a couple of examples. Clearly, the moving average filter as described above is stable. On the other hand, let us consider the following system. Let xn be 0 for all n that are negative, y minus 1 be 0, and yns be defined as follows. From the above equation, we can see that yn is equal to xk, k equals to 0 to n for all n greater than or equal to 0. As we see the feature of the system, it's called accumulator. Naturally, this is called an accumulator. The accumulator is an unstable system. Is unstable. For instance, if we give it as input the unit step signal, so if xn is un for all n greater than or equal to 0, then we see that yn is n plus 1, which clearly grows unboundedly as we increase n. So while xn is bounded, yn is not. What is the continuous time counterpart of accumulator? It's called integrator. Continuous time counterpart or analog of accumulator, it's called integrator, and it's described by following differential equation. As accumulator, this is also unstable. For instance, we can give xt, we can set xt to be unit step function and can observe that yt grows unboundedly. Next very important property that we will see is linearity. A system is called linear if it satisfies the following two conditions. What are the two conditions? The first one is scaling. It says that if xt results in input xt results in output yt, then for a constant, any constant a great a, for any constant a of xt would result in output a of yt. Let me write it clearly. A of xt would result in an output a of yt. And what is the second condition? The second condition is called superposition. It says that if x1t, input x1t results in output y1t and x2t results in output y2t, then x1t plus x2t would result in y1t plus y2t. Let us see a few examples and non-examples of the linear systems. However, before that, I would mention an important fact that if a system, if the input to a linear system is 0, its output must also be 0. If the input to a linear system is 0, its output must also be 0. This property can be inferred from the above two conditions. Okay, now coming to examples. It can be easily verified that the moving average system is linear. On the other hand, if I consider a continuous time signal system, where output is square of the input, so yt is x square t for all t is not linear. Okay. Let's now look at another property called time invariance. A system is called time invariant if a time shift in the input results in an identical time shift in the output. Results in an identical time shift in the output. More precisely, if input xt results in output yt, then xt minus t, capital T, would result in output yt minus capital T for any t, for any capital T. Okay. Again, examples. The moving average system described above is time invariant. Because the rule for generating the output that does not change with time. On the other hand, if you look at the discrete time system, yn is m times xn, this is clearly not time invariant. We now arrive at the most important class of systems, namely linear time invariant systems. As the name suggests, a system that is both linear and time invariant is referred to as LTI system. So these systems in short are called LTI systems. These are systems that are both linear and time invariant. These are most tractable systems. In particular, they have the remarkable property that knowing the response to a unit impulse input is enough to compute the response to any other input. Let's see what I mean. What I mean that if there is a linear time invariant system, say it's a discrete time linear time invariant system, and we give it input delta n and the output say is hn. This is unit impulse. This output is called impulse response. Then for an arbitrary input, the output can be computed using hn. More precisely, now I give the same system input xn, the output yn turns out to be k from minus infinity to infinity xk hn minus k. The operation that outputs yn from hn and xn, this is called convolution of xn and hn. This operation is called convolution of xn and hn, and it's denoted as hn x star hn. Okay, so to be precise, x star hn is k from minus infinity to infinity xk hn minus k. Okay, let's see a couple of examples. For the accumulator system that we saw earlier, the unit step response turns out to be un. For the accumulator system, so this is discrete time accumulator. if we give it a unit impulse input, the output Hn turns out to be Un. Okay, so impulse response of discrete time accumulator is Un. Clearly, for any input Xn to this accumulator, the output Yn can be obtained as Xn star. X star Un. Okay. On the other hand, if we consider the following system, let's consider this discrete time system where Yn is median of the three input values, namely Xn minus 1, Xn and Xn plus 1. This is called median filter. Okay. Its unit impulse response is an all zero signal, an identically zero signal. To see this, observe that if I input the following signal to this filter, this is unit impulse, the output of the filter will be identically zero. So Hn is 0 for all n. However, in such a system, observe that it's a non-linear system. So in such a system, I do not expect to have the following relation satisfied. Not satisfied. This is not satisfied because the system is non-linear. We now see some of the properties of convolution operation and also their implication on LTI systems. So let us see the properties. The first properties of convolution. The first property is unit impulse is the identity element of convolution operation. What this means is that if we convolve a signal X with unit impulse, the operation outputs X itself. Second property is convolution of a signal with a shifted impulse, shift the signal with a shifted impulse shifts the signal. Mathematically, convolution of X n and delta n minus n shifted impulse is Xn minus n. Okay. The third property is so-called distributive property. Its says that convolution of x with h1 plus h2 equals convolution of x and h1 plus convolution of x and h2. The distributive property implies that the parallel combination of two LTI systems, let's say h1 and h2, with impulse can be represented as an equivalent LTI system with impulse response h1 plus h2. So that is, if we input signal xn and we look at the sum of the outputs, call that yn, this would be same as the output of the following system: h1 plus h2 xn yn. So these two systems are equivalent. The fourth property is associative property. This says that convolution of x with h1 star h2 is same as convolution of x and h1 convolved with h2. Again, the implication of this property for LTI systems is that we can combine series interconnection of two LTI systems with impulse response as h1 and h2 into an equivalent LTI system with impulse response h1 convolved with h2. So that is, if we give input xn to the system on the left hand side, then it will produce the same output as if we have given xn to the system on the right hand side. Okay. The fifth property is commutative property. This says that x convolved with h is same as h convolved with x. If we combine this property with the associative property, we see that swapping two LTI systems in a series interconnection results in an identical system. So what we mean that if we have two LTI systems in series interconnection, then associative property would imply that the system is equivalent to this, and further using commutative property we can conclude that these two are same. Appealing to associative property once more, we see that the system that we began with is identical to this system. So that is, swapping the two systems in series interconnection does not have any impact. Okay. Next, we will see whether we can determine causality and stability of linear time invariant systems from their impulse response. We expect this to be the case since impulse response fully characterizes LTI systems. Let's see how causality and stability are determined based on impulse responses. Okay, so determining causality and stability from from the impulse response. We find that a discrete time LTI system is causal if and only if impulse response is 0 for all negative values of the argument. That is, a discrete time LTI system is causal if and only if Hn is 0 for all n less than 0. Let's see an example. Recall the moving average system. Where the output was yn was 1/3 of xn minus 1 plus xn plus xn plus 1. Let's see what is the impulse response of this system. Here is unit impulse. If we input this to the moving average system, the output is the following signal. Okay, so this is Hn. Clearly, H minus 1 is greater than 0. Then from the above fact, we see that moving average system is non-causal. Is non-causal. Let's see another example, and this is the accumulator system. We know that the impulse response of the accumulator system is un. Clearly Hn is 0 for all n less than 0, so accumulator system is causal. Okay, next we move to property to see how is property of stability related to impulse response. A discrete time LTI system is stable if and only if the impulse response satisfies the following property. The absolute sum of the terms of impulse response is finite. Okay, again let's see examples. Let's again consider the moving average system. For this system, if we compute the sum as needed to check stability, it can be easily seen that this sum is equal to 1, which is finite. So moving average system is stable. On the other hand, if you look at accumulator system, then this sum is clearly infinity, and so accumulator is not stable. Until now we looked at linear time invariant discrete time systems. Let us now focus on continuous time systems. Continuous time LTI systems. As stated before, a continuous time system is linear time invariant if it is both linear and time invariant. Let us focus on the following signal, which is called following pulse signal, which will help us define convolution integral. So we define a signal, a pulse. So define a pulse delta, capital delta of t as follows. It has width delta and height 1 over delta. Right? So this is 1 over delta for t in 0 to delta, and it's 0 otherwise. Notice that the area of this pulse is unit. Right? In continuous time, the unit impulse is defined as the limit of this function as delta goes to 0. Continuous time, unit impulse is defined as limit delta tends to 0 pulse signal. Notice that the area underneath remains unity. Okay. Here are a few properties of unit impulse in continuous time. They are analogous to corresponding properties in discrete time. Okay. The second property is, if we multiply ft with a time shifted unit impulse, the result is given by this expression. Okay, so these are true for all f. For all f. Okay. Now, having defined the unit impulse in continuous time, we have the following notion of impulse response. Okay. So we have a continuous time system. Continuous time system. To which we give input delta t. The output of the system with input delta t, denoted at ht, is called the impulse response. This is called impulse response. Further, if the system is LTI, that is linear time invariant, then output corresponding to output for any input any input xt can be obtained as yt equals to minus infinity to infinity x tau ht minus tau d tau. This is the result. This analogous to convolution in discrete time, and this integral itself is called convolution integral. Convolution integral poses similar properties to discrete time convolution sum. In particular, it has the following properties of convolution integral. First one is unit impulse is the identity element, that is x star delta t is equal to xt. The second property says that convolution with shifted unit impulse results in shifting the input signal. As for discrete time, we have commutative properties, that is x star of h is h star of x. Distributive properties, and associative property. Okay. Moreover, we can again write the characterization of causality and stability of linear time invariant systems in terms of impulse response. To be precise, causality of a continuous time LTI system is equivalent to a continuous time LTI system is causal if and only if ht is 0 for all t less than 0. Similarly, a continuous time LTI system is stable if and only if this integral h tau mod integrated from minus infinity to infinity is finite. Okay. Having seen this, next we will see the connection between linear time invariance and systems described by differential and difference equations. Okay. So the next topic is LTI systems described by differential equations. Let's say differential or difference equations. Let us consider a system, discrete time system, let's say. Discrete time system. Whose output is yn for input xn, and moreover xn and yn are related as follows. K equals to 0 to n ak yn minus k is equal to k equals to 0 to m bk x n minus k. Okay, this equation is called a differential equation. Then this system is linear time invariant if the following condition holds. The system is linear time invariant if y minus 1 equals to y minus 2 dot 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 equal to y minus capital N, all these are 0. Let's see an example. Let us consider the accumulator system. Okay, recall that in the accumulator system yn is equal to xn plus yn minus 1 for all n. Hence, if xn is 0 for all n, then we find that y0 is equal to y minus 1. In fact, yn is equal to y minus 1 for all n greater than or equal to 0. Okay. So this system is not LTI, linear time invariant. Let us now see a continuous time system. So here it is. We have a continuous time system. Its input is xt and output is yt. And say yt and xt are related as follows. So k equals to 0 to n ak dkyt over dt is equal to k equals to 0 to m bk dk xt over dt. Again, it turns out that the system is linear time invariant if all the initial conditions are 0. If the system is LTI, if y0 equal to dy over dt 0 dot 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 dy n minus 1 dn minus 1y over dt n minus 1 at 0 is 0. We can use this criteria to see that the RC system that we had seen earlier as an example of continuous time system is not LTI until y0 is 0. So example, let's see this RC system with input xt and the output voltage across the capacitor. Notice that here input and output are related by c dy over dt is minus y plus x divided by r. It can be checked that if xt is 0, identically yt can be written as y0 e power minus t over rc, right? The system is linear time invariant only if y0 is 0. Finally, we look at special functions and their responses to linear time invariant systems, and these special functions are called complex exponentials. Let's see what are complex exponentials in both discontinuous and discrete domain. Complex exponentials. Okay, let S be a complex number. Signals of the form e power st are called complex exponentials in continuous domain. So notice that this xt can also be written as, if S is sigma plus j omega, then this xt turns out to be e raised to sigma t times e raised to j omega t. Similarly, if you look in discrete domain, so this was in continuous time, in discrete time signals of the form xn equals to zn, where z is again complex, are called discrete time complex exponentials. So notice that if z is equal to s again r e j omega, if z is r e raised to j omega, then xn turns out to be r n e raised to j omega n. Now let's see what are the responses of LTI systems to these signals. First we will consider a continuous time system. Okay, so here is a system with impulse response ht. We give it a signal e raised to st. Then its output, from what we have learned, can be written as convolution integral of ht and e raised to st minus tau. It can be easily seen that this integral equals minus infinity to infinity this is h tau e raised to minus s tau d tau times e raised to st. Okay, we see that the response of the LTI system to the complex exponential is same complex exponential scaled by a constant. The response is the same complex exponential e raised to st multiplied by a constant. The constant here is called function. This constant is denoted as hs and is called transfer function. Okay. Let's see what happens in discrete time. Here again let us consider a system with impulse response Hn. If we input z raised to n, the output of the system yn can be written as convolution sum k equals to minus infinity to infinity hk zn minus k, which in turn can be written as k equals to minus infinity to infinity hk z minus k, and zn is out. So we again see that the output is a constant multiplied by the same constant, complex exponential. This constant, now denoted by hz, is again called transfer function of the discrete time system. Sometimes these transfer functions are called system functions. Let's see an example. Okay. Let us consider a system whose output yt to input xt is xt minus 3. Okay. Let's see how do you compute its transfer function. Okay. So we know that transfer function is obtained by inputting to the system the special complex exponential e raised to st. So what will the output be? If we input x e raised to st, the output will be e raised to s t minus 3, which we can write as e raised to minus 3s e raised to st. Clearly e raised to minus 3s is the transfer function. The same transfer function can also be obtained using the formula that we have derived above. We can also obtain it as hs equals to, let's see the formula that we minus infinity to infinity del tau minus 3 e raised to minus s tau d tau, which again turns out to be e raised to minus 3s as expected. Notice that we write del tau minus 3 because unit impulse response of the system h tau was del tau minus 3. Okay. Finally, let us look at a special case of this complex exponential application of complex exponential. A special case where s has only complex part, s is j omega. In this case, my xt, which used to be e raised to st, would be e raised to j omega t, and the output will be h of j omega, the constant factor, times e raised to j omega t, that is the input signal. This h of j omega can be obtained as follows. It can be obtained using the formula that we just derived. It will be e raised to minus j omega tau d tau, and this function h of j omega is called frequency response. Similarly, in discrete time, if we set z equals to e raised to j omega not having any real part, then again I can write yn equals to h e j omega e raised to j omega n, where h e raised to j omega will be obtained using the formula hk e raised to minus j omega k. Again, This function is called frequency response in discrete time system. This completes the first module of, or rather first part of our module on signals and system. Next time when we meet, we will see Fourier transforms, Fourier series, etc. Thank you.